Any questions from last time?
I have a question.
Speak louder.
Do generalized free fields, they satisfy equation of motion or what kind of field?
So you construct them so that generalized free fields satisfy equations of motion in the bulk. Yeah, so in so generalized free fields, this is okay. So we are going back a few lectures. So generalized free fields are basically, at least in the scenarios that we are talking about, they are basically single trace sector of some large N gauge theory. So in that sense, they don't have to satisfy any equations of motion. Okay, but they do kind of, by acting with because they have this Wick contraction structure, and so they give rise to the right correlation functions. Basically the 2-point functions are non-trivial, but the n-point functions can be constructed from the 2-point functions using Wick's theorem. So that's essentially the defining property of generalized free fields. So what you can think of, at least the basic ingredients of holography, as the statement that these non-trivial 2-point functions can be engineered using a equation of motion in some higher dimensional space. Okay, so there is, if you just look at it in terms of a 2-point function, 2-point functions in a standard conformal field theory, they basically do not, you can't, it's except for the case of free massless field where the 2-point function is, the scaling dimension is d minus 2 by 2, then you can write it as an equation of motion solution. But typically, if you just because the 2-point function will have some non-trivial form. So 2-point function will be 1 by x minus y to power some scaling dimension. So that you cannot write as the solution of an equation of motion in the boundary theory directly. So what you can do is you can write it as a in terms of an equation of motion in ADS, and then you can get this in some indirect mechanism, and that's essentially what the holography the holographic correspondences, if you like. So that's kind of a slightly, if some of you did not follow it, we will basically talk about holography later. But since I mentioned generalized free fields, I just, you can go look it up on the video if you, later on if you're not very clear. So I don't want to elaborate it on too much. I mean, probably some of you may have not fully understood that, but it doesn't matter, okay? Okay, so any other question from last time? So the last time what we did, let me give a brief recap since there are so many holidays and everything. So, and tomorrow is also a holiday, right? So what we'll do is and next Tuesday is not good for me. So what we'll do is we'll have a lecture also on the next Wednesday. Okay, so next Wednesday exactly the same time we'll have the other lecture, and Thursday we will have as normal, and we need to make up 2 classes because 2 working days we missed. So at some point we will do that, and I think it will be necessary because we are kind of a little bit behind. Okay, so so what we talked about last time was this question of Hawking radiation, and we sort of started talking about that in the setting of we solved the wave equation and we have set all the preliminary ingredients in place. So this is what we have done in the last lecture. And today I think what we will do is, so we can just put things together and for the collapsing black hole, the context in which Hawking originally did his calculation, and we will get the answer, we will get the thermal answer, and we will say a few more words. So this is what we are going to do. Okay, so most of the hard work in some sense we have already done. So, and we will kind of skip over the way in which Hawking did the calculation to kind of, so you will see. So let me just draw the Penrose diagram of a collapsing black hole. So this we drew at the end of the last lecture. So as I said, this is kind of a heuristic, picture, because we can't really draw a picture like this when there is matter in the geometry and things are collapsing and so on. So typically in Hawking's paper, you can see pictures of this kind. I don't know whether that's the first place where these pictures first showed up, but at least it is the one to use it in a useful way. Okay, so this is the standard picture. So this is the horizon, and this is some collapsing star. Okay, and as I said, we want to simplify this even further by making it into a collapsing null shell. Okay, so the null shell is basically something that so you launch your a massive shell at some point, and it basically collapses, and if your initial conditions are such that it falls in, then essentially as long as it has energy momentum tensor, it can still form a black hole. Okay, so this crucially presupposes the fact that there is nothing special happening at the horizon. For instance, the shell passes its this is the place where the shell is passing its own horizon. Okay, but note that it's not there that the event horizon was started. Event horizon was started before that. Okay, so that's the nature of the event horizon. It's a teleological surface, etc. I mentioned it briefly. So it's because it's a global object. Okay, so this is the picture of. This is the picture that I drew last time. So this is the picture of a collapsing shell of radiation, if you like. Okay, it's a collapsing shell of massless, sometimes called null shell. Okay, so and this is a simple example of what is called a Vaidya spacetime. Okay, Vaidya spacetimes are spacetimes where there is some dynamical collapsing stuff happening, and usually in some null direction. And it doesn't have to be, but this is an example of a simple Vaidya spacetime. Okay, and the advantage of this picture is that we can sort of cleanly disentangle where the black hole begins and where the Minkowski space is. So here there is some confusion about there is never really clean Minkowski space anywhere, right? Because the geometry, even though this is conformally, this is kind of Minkowski, at this part there is still the solution is Schwarzschild. It's just that the horizon hasn't started yet. So roughly speaking, the outside region is Schwarzschild, and in interior you have to put in some other metric, and etc., which are all like kind of uncontrolled and ugly things. Okay, so that's the advantage. The advantage of this is that because essentially we have split the problem into two pieces. Here we know that the metric has to be Schwarzschild. Why? Because it is the metric of a spherically symmetric object. There might be something in the interior, but that doesn't matter. As long as we have spherical symmetry, we know that the metric is Schwarzschild because of something called Birkhoff's theorem in general relativity. Okay, so this Schwarzschild because of Birkhoff's theorem. So that's a statement that it doesn't matter whether it's, as long as the pulsations or movements of matter are radially symmetric, the metric outside the matter is always Schwarzschild. Okay, so even if you have some shell falling in, as long as it is spherically symmetric outside, this region is still is conventional Schwarzschild, this entire region here. Okay, so this region on the other hand, because there is no mass as seen from infinity, it's Minkowski. So we have basically went from an ugly mess which involves some collapsing star and all that to a clean problem which splits it into two pieces. One where there is pure Minkowski and one where there is Schwarzschild. And the assumption here is that none of the complications actually matter, and all that matters is the fact that the Schwarzschild, there is some collapsing object can still reproduce the conventional, all the things that we'll see in Hawking radiation. Okay, or another way of saying the same thing is that essentially what we are assuming is that there is no particular structure happening at the horizon, which is somewhat part of the assumption here as well. Okay, so the smoothness of the horizon is fundamentally what is responsible for, it's not obvious here, but in Hawking's calculation he essentially only uses, it turns out that the structure at the horizon is irrelevant for the final conclusion that he draws. Okay, so here it might seem like, oh, something is happening at the horizon maybe, because there is a star and so on and so forth. But it turns out that the approximation that he makes in order to get the answer, which I will talk about in a little bit, is irrelevant, is insensitive to the matter that is there. So because of which we are now we are using that as a message and kind of idealizing it into one step and saying that, okay, you have a collapsing shell, then we have this collapsing shell of null shell, then all that we want can be understood from here. So this is the setup. Okay, any questions? So this is my null shell. This is Schwarzschild. This is Minkowski. This region means everything here is Minkowski. Okay, so this whole region is Minkowski. Essentially because there is no mass inside at that point. Okay, so if it is again because of Birkhoff's theorem, this whole region is Minkowski because of Birkhoff's theorem, there's no mass. This whole region is Schwarzschild with finite mass because of Birkhoff's theorem. Okay, so so the thing that we want to do, so ideally what we would like to do is we would like to start with Minkowski space, so we know what the vacuum state in Minkowski space is if you have a scalar field. So you quantize a scalar field and the vacuum state in Minkowski space is something we know. Okay, either in path integral language, we wrote it in various forms and so on. So there are some Minkowski modes that we start with here, and then the question is, as you evolve, once the horizon is formed, and what happens? So if you start with a Minkowski vacuum here, and later on some collapsing shell falls through this, then what happens at infinity in the future? That is the question. Okay, so if you start with Minkowski here and you find radiation here, that's a proof of Hawking radiation. Okay, so that's a possibility because the space-time has changed. So even though you started with what you thought was the vacuum state, because the modes, we discussed the fact that ground states are defined by modes. Okay, so the ground state of a scalar field on a Schwarzschild background need not be expressible in terms of just purely the Minkowski vacuum if you expand these modes in terms of this. Is that statement clear? So what I'm saying is, like, you have a ground state, some set of modes here, which is basically some solutions of free wave equations in Minkowski, and you have two sets, you have a set of modes which is Minkowski modes, the standard ones, e to the minus chi k omega, omega minus omega times t minus r, whatever. Okay, so if it is massless. So, and similarly there will be some other solutions here, but here you have to solve the things that I did yesterday. You have to solve the radial Schwarzschild equation, which I call the Reggie-Wheeler equation. Okay, so that if you solve, you'll get some set of other modes. So the question is, if you have a solution of a Minkowski, what corresponds to Minkowski vacuum here, does it translate to a vacuum here, is the question. And the answer is fundamentally no, is the reason why Hawking radiation exists. Okay, so so this is our premise. So we want to start with Minkowski vacuum. In the past means this region, and figure out essentially here somewhere, and figure out what the final state is in the future. Okay, so this is what we want to do, and all of them for the scalar field. So for a massless scalar field. So the Minkowski annihilation operators will annihilate our initial state. That's what it means that we are starting with a vacuum. Okay, Minkowski vacuum. So, but the point is that if you try to write that Minkowski annihilation guy, which is, let's say, A, omega, L, M, etc., Minkowski, this will contain Schwarzschild, let me call it B Schwarzschild and B dagger of Schwarzschild. So the vacuum will be different, very roughly. Okay, that very crudely, that's the idea. So, yeah, and this is the place, so where, this is the place where, so in essence, we are not going to actually solve this problem in any real sense. Okay, what we are going to, like, very roughly, okay, let me say it another way. So, how would you compute? So essentially, so the way we are going to solve this problem is that we are going to guess the state of the state of the scalar field at, right after the shell has passed through. So this is what we are going to do. We are going to guess it. Okay, and then the point is that will serve as an initial condition problem for the Schrodinger potential that I wrote down earlier. Okay, so we had this. Okay, we had a potential like this. Okay, so this was the potential that we had. So this is the potential that we'll have for the Schwarzschild somewhere in, basically somewhere here. So essentially what we'll do is we'll guess the state of the scalar field here, and then we will do a scattering problem on this potential well and write down, because the scattering is essentially what is controlling what the final state would be here in the future infinity, so to speak. Okay, so we'll guess the state here, and then we'll just do sort of quantum mechanics 101 type of stuff in order to get the answer at infinity. So I should emphasize that the step that we are kind of, I wouldn't say it is like we are going to, it is guessing, but it's I don't think there is much more than the guess in any way of calculating that entity. You know what I'm saying? So I'm going to guess the answer here, and then we are going to propagate it through this potential barrier to get it here. Potential barrier propagation is sort of trivial. It just what it does is that because of the potential barrier, there will be some backscattering from the barrier. So I mean, it's in some sense it's a more complicated part, but we are not very interested in it. We'll just write an expression for it, and that's what everybody does. And if there are specific things, if you want. So there, essentially, what it will do is that. We'll find that the thermality is happening in our assumption here. What we are going to do at the assumption here, and then we will propagate it through the barrier, and it will make it not exactly thermal by introducing what are called some gray body factors. Okay, so the gray body factors basically correspond to the fact that there is some backscattering. So from the potential, so you are sort of thinking of some initial state here, and then it gets backscattered. So it's not exactly thermal when seen from infinity at late times. Okay, so that's the nature of the calculation. So Hawking basically what he did was he made some assumptions for how to guess. He kind of rationalized this the guess of the state. Okay, so but that's a questionable in many ways in some, so it's a very clever calculation, but at the same time it's also not completely, it's not clear whether it is fully defensible. And the way he did it is that he essentially drew the same conclusion that we are going to put in our initial conditions here, which is basically at the moment of horizon crossing. So the way he does that is by coming to this conclusion that no matter what happened during the collapse, it is, this modes that you find at late times, which is what we are interested in, because the black hole is formed and it has kind of settled into its final state, classically, after collapse, etc., it has settled into its final state, and we are looking at some late times. We are looking at what kind of radiation do we get at infinity. That's what we are looking at. So this means that, so his claim is essentially that it is the modes that are stuck close to the horizon, so essentially like, what is a good way to draw this picture? So the idea is that, it's during the time of horizon formation, the modes that, okay, let me just draw this picture that sometimes Penrose draws. So this is, sorry. So, so there is collapse here. So this is the singularity. And the idea is that, so this is sort of like a more physical picture of the same setting. Okay, so there is some collapsing shell coming here. Here I'm thinking of it as more matter. I'm not drawing it in. If you want, you can make it null like this if you like. Okay, it doesn't really matter. Okay, so and the horizon is forming somewhere around here and the singularity is here. Okay, so the picture is a little bit, you have to kind of interpret it correctly. So let me not talk too much about why the singularity is drawn vertically here. But the thing that matters for our current discussion is that if you have, let's say, so the horizon looks like what? So I think this is the horizon. So the point is that, like, if you have, is that the correct picture? Am I drawing it wrong? So this is why I thought of saying it one way and I decided to change it midway after I started the lecture. So let me, so you have, no, I think it is like this. Yeah, so this is your collapsing stuff. You have this, and the horizon is essentially forming like this, I think. Is that, somebody can, is that reasonable? Because this has to be null. And let me not say it this way. I just wanted to make one qualitative statement because I think there is some picture here. I think I'm doing something wrong here. So what I want to say is the only fact I wanted to emphasize is that it is those high energy modes which are stuck near the horizon at the, right before, if you fall into the black hole, it is those modes which are stuck by the horizon during the horizon formation time that you see at late times. Is that statement clear? Like if you see the only modes that you will see, because the black hole is, like whatever falls in is, just falls in, but only those modes which are stuck close to the horizon during the horizon formation period, those are the ones that are going to get redshifted and you're going to see it at late times. Okay? So, and those modes are necessarily those modes which are very high energy in their initial state. Okay, they are very high energy, that's why they are redshifted and they are still visible. So they are essentially horizon straddling surface. The horizon straddling, let me draw the horizon this way, but I don't like drawing the horizon this way because I feel like it should have been null in this picture, but let me draw it from my memory. So it's some collapse, and the point is that it is those, let's say you have a mode coming in from here, and it's something that straddles here and then goes like this at late times. Okay, so this is the horizon. So the modes of a particle or a low, high energy mode that's almost caught by the horizon is the one that you see at late times. So this was the intuition of Hawking. Okay, so and I think this picture is correct. Something about this horizon doesn't make me completely happy, but let's believe it for now. Okay. So I feel like this horizon should have been null in some way, but maybe I'm thinking about it wrong. So, but yeah, so anyway, so there is some collapse and the horizon forms here, and the scalar particles, the scalar waves that are coming in, They are coming in and they're almost straddled, caught by the horizon, and then eventually they will escape, and those are the ones that you detect at late times. Once the black hole, the ring down or whatever, the intermediate time scales have settled in. Okay, so the black hole forms, it does whatever it does to do, and it has a ring down phase, and then it settles down. Okay, so at that phase, the ones that were almost caught by the horizon are the ones that you see later. And so that means that when it started, it had very, very high energies. So in fact, you can show that the modes that you see at late times are trans-Planckian in energy. So they have higher than Planckian energies. So that makes whether this calculation is questionable or not, that's a question one could ask. So, but the primary point I want to make is that because they are high energy modes, he could assume that they are not really affected by the matter that it is passing through. Okay, so you could make an approximation, essentially a WKB or particle, what is it called, optics approximation, that the particle passes essentially through geodesics in that this thing, and using that he could justify the assumption that I'm going to make now. Okay, so partially because the initial assumption whether this approximation is very valuable is unclear now. I'm not going to do it. We'll just write down based on whatever we have understood about Hawking radiation now, or all the stuff that we have done. We'll just guess this answer. Okay, so that's what we are going to do. Is that clear? So we could somehow pretend that we are doing a more rigorous calculation, but the rigor of that calculation is not that clear. So which is also one reason why it is okay to sort of guess this. But I want to emphasize that once that guess is made, the rest is just scattering in some simple potential, and that's not where the physics is. Even though today I will spend a bit of time talking about that, I really want to emphasize that this is the place where the money is coming in. You know what I'm saying? So this is the real the assumption or the result in some sense. And after that, we will do this scattering in this classical potential around a black hole, and you will see that there is some backscattering, and so because of which the perfectly thermal radiation becomes slightly corrupted, and you have a gray body factor in the result. Yeah.
The initial inertia will have very high energy. That's why we are able to observe.
This doesn't have to have, it can be arbitrarily low energy, right? Yeah, so as long as it is focused in some way so that it just goes in, right? I mean, also the energy density, so let me put it this way. So as long as the total energy is sufficiently high, the black hole forms at very low densities. You see what I'm saying? Because the density of the black hole is m by roughly speaking m by 4 pi r cube or something, right? And r is like m, so it basically goes to some inverse power of m at the time of horizon formation. So which means that I can create this black hole by starting with, as long as it has enough energy, I don't have to be in this place. It seems like a very classically accessible place. Because there is no high densities, high curvatures, it doesn't have to happen. Okay, so for instance, for astrophysical black holes, it is fairly, it's a fairly intense place, but it doesn't have to be. At least in principle, that's what we believe. Okay, because it doesn't look like general relativity has any real problem at the horizon. So which means that you start with sufficiently energetic null shell. It can be crossing the horizon. And this is the statement that some people usually make, that we could be passing through the horizon of a gigantic black hole right now and we would not know it. Because as long as the mass is sufficiently high, the density can be arbitrarily low. That's the point. So the density of energy contained in that space-time volume. Okay, so this is why it is reasonable, or at least until it breaks and hits us in the face, which sometimes it does, we should treat this region as somehow smooth. Okay, so so that's the point. So yeah, any other question? I sort of bungled what I was saying here, but I think this final picture may be correct. But anyway, the philosophy, the idea is that, so the idea that Hawking exploited was that it's very high energy modes which are basically seen by a late time observer. That is the assumption. Because if the mode gets caught up inside the horizon, then you're not going to see it in the future infinity. Here you will not see it, right? Somebody standing here will not see it, it will end up here. So if you're standing here and you're looking at these modes, the only modes that you will see at late times are basically these ones. This is the claim. Okay, so about everything else, it will basically have gone inside. Okay, so the point is that why it is late time. Of course, you could have had some low energy modes coming here, etc. But our assumption is that all the quasi-static dynamics have settled down. So there is nothing else left. So the only possible modes that you'll see in future infinity are basically the ones which were almost caught by the black hole. So that's the assumption. Okay. Okay. So right. So let me write down this. So this guess for what the state is. Yeah. So the point is that you have these set of modes. Let me draw that picture one more time. Okay. So we have this shell, and what we are interested in computing. So this is the final modes that we are interested in capturing are the things that will get here at infinity, and what we want to understand is, so if you really wanted to do a proper calculation, what you would do is you would decide what the modes are in the past here, etc., etc. But what I'm going to do is make a statement about the modes here. Okay. So and those are modes. The reason why I can make a statement about them is because from here, so I make the assumption that these modes are unaffected, are just going to stay in the vacuum of my Schwarzschild. Okay, that's natural, because this is, if you remember from the picture I drew last time in the Kruskal case, which is what so there were 4 kinds of modes that I wrote, right? Okay. So if I assume that there is something coming in from here, then it's not very interesting. It's not a universal answer what I get here. I want to assume that nothing is coming in from here and then see what happens here. Okay, so this is why I'm assuming that the modes coming in from here are in the ground state of the Schwarzschild space, Schwarzschild solution. Okay, the wave equation F. I wrote an F omega Lm last time. Okay, so these guys are in the ground state, so there's nothing there. So, and the second guy, so there are essentially what I need to specify in order to define this Schrodinger scattering problem is that I have to tell you what the modes here are and what the modes here are. Okay, so here I'm saying that there is nothing coming in, and here what I'm going to say is that this is going to be the same modes that you get by computing the how so when we had the, let's say, Minkowski or even Hartle-Hawking thing. So we did this, so we had a Rindler-like modes here, and so this whole thing can be thought of as a Minkowski vacuum, and we could compute a thermal density matrix by tracing over this left half. And the real motivation for doing that was that this system, the vacuum state, was entangled. Right? So between the left and right guys, and then we traced over the left guys to get the density matrix here. So the assumption, so that why is the vacuum state entangled? Vacuum state is entangled because this is the Minkowski space. Okay, or if this is the Minkowski space, or it doesn't matter, but the same thing. Okay, and so I traced over this guy and found the density matrix here. So if I assume again, so that entanglement, what does that really mean? That entanglement is basically what makes my space-time Minkowski. It means that 2 Rindler wedges can be put together into a Minkowski space if and only if you like, if if there is entanglement of the stuff kind that I found when I did my path integral. Okay, is that clear? So essentially the statement is that if you write down the Minkowski vacuum, you have e to the minus pi omega I left, I right. Okay, so this is what I had. If you remember, this is omega I. Okay, so this is what I had, and if I trace it over on one side, I got one density matrix on the other side. Okay, so that's the expression that I got on the right side. And the claim that I'm going to make here is that because I expect this region of space to be smooth and locally like Minkowski, I am going to declare that the incoming modes from here should basically be of the same form. Okay, I'm going to demand that the full state that I'm going to write down is going to be, so if you like, is omega, so this is the ground state, and this is coming from the ingoing part, and then there is the omega Lm. So this is something that I wrote down before. I'm just repeating what I wrote and then giving you some reasons to believe it. Okay, so this is the state that I'm working with. So the way you should think about it is that if I want to specify, a sort of a scattering problem in 1 plus 1 dimension, so 0 plus 1 dimensions in quantum mechanics, is I have to specify what my initial, sort of the initial states are. They're not fully eigenstates because I'm solving a problem for, a potential which doesn't know about it, the free particles here and the free particles here, and then I say that, okay, these are the initial conditions I'm going to put in, and then what is going to be the final configuration. Okay, but you should understand that you are, this initial condition and this initial condition are for the sort of the free particle approximation. Okay, and that's essentially what we are doing here. Okay, we are saying that this together with this is my initial assumption for what the field here would be, and then I have to solve the Schrodinger problem with this potential in order to fully determine what the final stationary state is. Is that statement clear? That's also another important step, because what these states actually mean is that, so this is not to say that, so that's the reason why we need to still solve this potential problem. That's how we are getting the final eigenstates of the problem, are by solving it with this potential and getting the full back scattered problem. So that is the step where we need to really solve one more Schrodinger problem. But my claim is that this is the setup. This is the step at which the real most important ingredient has gone in. Is that fine? I can take questions if you're confused, because there are a few different assumptions, approximations, etc., that are going in, and I don't think I explained it as well as I should have. Yeah, so let me just say it one more time. So the point is, we need to specify this initial condition for our scattering problem. But remember that Schrodinger equations, what we really mean by scattering problem is that we are saying what the initial condition for the free part of the problem is. What we are ultimately really interested in is computing the stationary state. Okay, so that's what we are really doing. So what we are saying is that the free part of the problem, this is what we are going to specify. And then we will solve for this scattering part or the potential part by doing the standard Schrodinger thing, which I will do in a second. Okay, so that's the part which is technically a little bit annoying, but this is the part which is conceptually more important.
So the Hartle-Hawking state is further which?
So the Hartle-Hawking state hasn't gone into it. What I have done is that I know that the Hartle-Hawking state, if it existed, it should have been this entangled state. Okay, and essentially what the statement is that here I am assuming that the space-time is locally essentially Minkowski. That's that's essentially the assumption that I'm making even in the Hartle-Hawking problem. I'm saying that, okay, here the space-time is locally Minkowski, and I'm saying that because of which I can write down my the vacuum state of the full guy should be this entangled state, and since I'm only looking at this part, right? So this is the only region I have access to. There is a horizon here, there is the only region that I have access to, which forces me to trace over the stuff on the left side. So this is the natural density matrix. So that's why my initial state is already a density matrix. Okay? So it is, by the time, the initial state that I'm putting in here is already a density matrix. Okay? So that's essentially, you can think of it as coming from this sort of thing. So the same reason why the Unruh vacuum that looks like a density matrix is the reason why this initial state is a density matrix. Okay? So, so that's what that is. And this state, for obvious reasons, is called the Unruh state. Or Unruh state. So what we are essentially doing is that we are assuming that, this is a vacuum state for a collapsing black hole, collapsing matter in a black hole. So the assumption is that the ingoing states are in the vacuum, but the outgoing states are in this thermal state. Okay, so that state is what is called the Unruh state. So this is my initial condition for the Schrodinger scattering problem. So now if that is clear, I think the rest is more or less, it's not, I mean, you can just write down the answer directly if you want, but I'm trying to follow Harlow as I said. So let's do a little calculation. Okay, so any questions? Yeah, so now we want to do is, we want to compute the energy flux at infinity using this as my initial condition for my scattering, and this I can compute. So let me write down an expression like this, and the expectation value is to be computed in that particular state. So what I have done is, so this is the definition of what the energy flux at infinity would be. Okay, so there is a stress energy tensor. So the stress energy tensor is, if you have not seen it, I mean, so yeah, so the stress energy tensor basically computes the flux of, if you have a stress energy tensor like this, you can think of it as the momentum flux in the p mu momentum flux in the v direction, nu direction. That's roughly what it means. And if you have not seen it, you can go look at Weinberg's cosmology book, not cosmology, the older book, Gravitation. He has a clean discussion of how stress tensors should look in special relativity. So if you have not seen it, I think that's a good place to look. But once you believe that, this is basically just T0R and the R square omega is the area. So you're computing the integral, and that's what the flux is. And this minus sign, I'm following the conventions of Harlow. Okay, choosing the normal, etc. So, so it depends on whether you're thinking of this energy as going out of the black hole or inside into the black hole. That's where this minus sign comes from. I can choose either one, depending on what I call what. Okay, so this, now you can explicitly compute. The stress tensor of a scalar field, I mean, exercise. So this, if you have not done it, I think it is a simple exercise. So T mu nu, compute T mu nu of a scalar field in living in a space-time with metric G mu nu. Okay?
This is just a continuity equation.
Yeah, I mean, you can think of it, yeah, I mean, sure. Yeah, but it's like, it's not even that, like, it's really just saying that the flux of some conserved quantity, it's just the energy momentum flux, right? I'm just literally computing the flux, and I'm saying that that's how much the energy would go down or increase.
Shouldn't we have covariant derivatives instead of normal derivatives? In GR, we have.
But this is asymptotically, this is an asymptotic thing, right? At infinity, it is still Minkowski time, essentially. So yeah, so I'm computing everything far away, some sufficiently far away place. So let's call it somewhere around here. Okay, so this is basically some r equals to constant slice. So an r equal to constant slice will basically look like this. And this r equal to constant I'm thinking of as very large. Okay, so this is r going to infinity. Okay, so, and the point is, so this you can compute and you will find some expression which contains two derivatives of the scalar. I mean, two means, products of one derivatives of scalar. Okay, so that's what you'll get. So this, if you have not seen, you can either look it up or you can do it. It's straightforward. You will need the scalar action and vary it with respect to the metric. Okay, so, and anyway, so here, that the claim is that this reduces to an expression of this form. Okay, so this expectation value is again to be computed here on this state. Okay, so the way we will do this, compute this flux, is that we will compute it for one particle state, and then so the n particles, essentially what we will have is we'll compute the expectation value of the number operator in this state, and then just multiply the flux of one with that expectation value. So that's what we're going to do. Okay, so let's do it. So phi dot dr phi is so on these guys there is nothing, it's just the ground state. So essentially I only have to compute it. I'm only computing it right now for a single particle state. I'm not even computing it for the full density matrix here. I'm just computing it for a one particle state. Okay, so and that one particle state basically means I'm starting with some A. Okay, A is basically the modes that generate this F guys. Okay, so A omega L M acting on the vacuum. Okay? So those are nothing but the vacuum of Schwarzschild in the exterior region. So when I say that 0 and these ends, all of these basically stand for the ground states of scalar fields in the exterior Schwarzschild geometry. Fine? So yeah, so if you have any questions, there are various places where there are small ingredients. So if you have any questions, just ask. So this is the one. So this is the one particle state. So I'm basically trying to calculate this quantity in a one particle state. So the claim is that if so this is the bra, and then there is also a ket, which is, there is also a dagger omega LM, a omega LM. So that basically, so this expression here is what is coming from the phi dot dr phi. Okay, if I plug in my mode expansion and compute it, this is the thing that will stay there. And I'm assuming normal ordering. So whenever I want to interpret this as an operator, I need to assume normal ordering. Okay, so and then it is acting on a dot this guy. So this is my object. Okay, so but this is, this is I should emphasize that this is just unnecessary fuss in some ways.
These are the creation and annihilation operators in the Schwarzschild.
Exactly. Yeah. So all of this, so all these states are in the Schwarzschild patch. Okay, and right, yeah. So the untrue state is basically, so in order to fully specify an initial condition, I should say what my past vacuum is, and that past vacuum is basically this and this. That's the statement. Okay, so the past vacuum is, you can think of it as, like you can do a very exactly similar calculation in the Kruskal patch as well. So let's say you have this. So what you would say is that my initial conditions here are, the initial state that I'm doing my calculation with is basically one where there is, these guys are in the ground state, so there is nothing here, and then there is something here coming at thermal, this thing, and then what I'm computing is the final state in this region in some sense. Okay, so this is something that I can calculate because that is just coming from scattering across the potential, which is outside of the black hole. Is that clear? So the philosophy is that, so this entire thing that you're doing now is in some sense the trivial part. That's how at least the way I think about it. Because all of this is, there is some complication, there is all kinds of things, and it is good to know it. And for instance, people always talk about, you start with this initial state and then what happens to the final state. But by the time you set up the initial state, you have essentially put in Hawking radiation. At least in this way of doing the calculation. In Hawking's calculation, of course, he had some justifications for it, which is what I explained in terms of this. But those justifications have sometimes been questioned. Other people say otherwise, etc., because of the presence of Transplanckian modes. Okay, you need these Transplanckian modes at early times in here. So the idea is that the modes that he's finding are the things that are coming in from here. Okay, so and those modes, by the time this is, when you pass through here, because there is a lot of redshift here. So this picture is kind of misleading in some sense, because this is a causal structure picture. Right? So there is actually these null rays are straddled close to the horizon for a very long time. So that's why they become redshifted and, at late time so that they become detectable. So, and because of that, there is actually there is a question of whether the initial state that you prepared for these guys, which is very high energy, is it trustable or not in some kind of, we are working with a semi-classical approximation, right? So should we worry about some quantum gravity things that you don't know, etc. So people have argued against this also, okay? So there are various arguments, but I'm just saying that in some sense, it's reasonable for various reasons. And the question is whether we trust it, but this is where we can start. This is a reasonable place to start our calculation. So, considering especially the fact that we did all the work in the setting of Minkowski and Schwarzschild and all that, eternal Schwarzschild and all that. Okay, so this guy, so now the point is we are interested in, the important thing is that we are interested in calculating it in the future, at the late times. So which means that our, the place where we are going to calculate this far away from the horizon, okay, these quantities we are computing at far away. So this is the flux at infinity. So this is R going to infinity. This is not something close to the horizon. So which means that we can treat these f omega LMs, these guys basically just become the Minkowski modes. Okay, but the crucial point is that it is not just any Minkowski mode, but there is also a transmission coefficient coming from the fact that these things are coming through this and going here. Right? So you have to by hand put in a transmission coefficient, which in principle, by looking at the modes and specifically and etc., people have tried to, you can calculate it. Okay, so there is the first person to really do it in great detail is I think Don Page. So he has papers from 1976 which he has done this in great detail, but we don't care. Okay, so this is as far as it's bookkeeping for our purposes mostly. So what we will do is we'll just keep the transmission coefficient as explicitly as a piece. So this is the transmission coefficient if you like, and then we have the outgoing modes at infinity, and then there is a root 2 omega because these are Minkowski normalized modes. Okay, they are far away. So these are effectively, they should become the what is it? The Klein-Gordon normalized modes in Minkowski space far away. So this is your T omega L, which I will call the transmission coefficient. Okay, so so there is, because the transmission coefficient, because of time reversal symmetry and all that, you can also think of it as an absorption coefficient for things coming from infinity. Okay, so people sometimes write this as P omega L, or more precisely, P absorption omega L is T omega L square. This is just quantum mechanics. Okay, if you had transmission in this way, the absorption probability or amplitude or whatever, you guys know this better than I do, I'm sure of this. So this is square of this. Okay, so sometimes we will use that change of name sometimes. That's the reason why I said it. So using this, now you can plug it into this. And note that because of these complex conjugations that are sitting here, only the absolute value of T omega will ultimately matter. Right? So these guys contain an F and an F star in each of these terms. So ultimately we only have the absolute value. So this is the reason why we will be able to just call it P abs omega L. Okay? So in other words, so plugging this into this, we can compute this to be equal to minus omega by r square okay. So this is my expression. And now, because we are interested in total, so this is just this guy, we want to integrate it across the whole angle, the solid angle, and this r square will cancel with this r square. Okay, so that's just because everything is massless, things die down as 1 by r square. So and then so then you integrate over this d omega, and if you integrate the d omega, this y lm y star lm, if you integrate it over d omega, you will find delta l prime, and so because L and L are the same, you will basically just get 1. Okay, so this is just a property of, I think there's a 1 by 4 pi sitting here, I think. Yeah. Okay, so so that's the, am I missing a 4 pi somewhere? So let me erase this. So the claim is that at the end of the day, you find so this whole thing. So if the claim that I want to make at the end is that this is equal to omega times P abs this. Okay. In fact, this will be minus because there is a relative minus sign coming from here. Am I missing a 4 pi there? I think. So can somebody look up what is the formula for this on Wikipedia? I'm sure if you look up spherical harmonics, you will find it. So there should be a d theta, d phi. D phi is from 0 to 2 pi, and this is from 0 to pi. And this is, I know that it is proportional to this, but is there a 1 by 4 pi here?
No, there is no one.
Ah, excellent. So then we win. So that's good. Huh?
0, 0 is 1 by square root of x.
Yeah, so I think that, yeah, perfect. So I think so this is our normalization. So so that means that there is no 1 by 4 pi and we win. So otherwise it would have been a 4 pi that I'll have to chase down. Yeah.
We don't care about normal ordering stuff in the diagram. Don't we like
We wrote it explicitly normal ordered. We wrote it explicitly normal ordered because, see, this guy is, note that this is not an energy momentum tensor, it's a scalar guy. It's not a classical object. We are computing a quantum stress tensor operator in the scalar field theory. So which means that because it's a free theory, we can normal order and get out of it. Okay? So actually the term that you're subtracting is actually infinite. So in some sense, so this is, you will have to justify it, and it has some physical, we will talk about it a little bit more at some point. But so the normal ordering by itself would not have been such a big deal, but the term that I'm secretly subtracting is actually infinite. Okay, but that is whether it matters, etc. So really there is a whole subject called stress tensor renormalization. So that one you have to be a little bit careful about, but the basic physics here is not really affected by it. So let me not emphasize it just now, but we'll probably come back to it at some point. Yeah, so this is my expression for the flux, and this was a calculation that I did for only one particle state. Okay, so now what I want to do is I want to compute it for a state where, for this state. Okay, and the easiest way to do it is basically just compute the expectation value of the number operator in this state. And this is a density matrix, so I can just compute it like this. So my normalization is this times the usual. Okay, and that gives me, okay. So all I have to do in order to get the final answer is that, so that's the place where this is not quite correct. This is, if I really want to think of this expectation values in the full density matrix, this calculation I've done only for the single particle case. Okay, so if I'm doing it for the full density matrix, the correct answer is d by dt is omega, let me write it as an integral, so this is sort of the final answer for the Hawking flux at infinity. Okay, note that it is, if you really still have to, if you really want to compute that quantity, you have to actually evaluate p-apps also. But I want to emphasize that that's purely a quantum mechanics problem, which you all in principle know how to do. Okay, so this quantity, but of course it's complicated by the fact that the scale of this potential was a complicated potential. It's not just some simple square, inverted square or something like that. So we'll have to work hard to figure out where exactly the energy is. So the real challenge in all these things is to figure out where this omega is, right? So if the omega is here, so then the information at that particular location of the potential will go into the calculation. So which means that you have to work hard if you want to keep track of the full omega information. Okay, so but we don't really care. So the final expression, as long as this is calculable, and it is, we know what it is. We can at best put it in a computer or something like that. Okay, so this is the sort of the final result. So I know that there are a few moving parts in it, and that is not really like that easy to do this calculation without getting into it. So if you have any questions, I can take some questions.
Sir, if we assume the ground state to have energy.
Ground state sorry?
To have energy.
Yeah.
Then it will also scatter.
Right. So, but we are doing this calculation in the ground, in the vacuum state of the field theory, right? So the assumption here is that we are working with a fixed background. Gravity has been turned off, right? So we are doing this calculation. So this is what I said, that G Newton, in the couple of lectures ago in the beginning, I described this, the assumption that we are making, that we are working in the limit where G Newton is going to 0, but R plus is held fixed, so that the mass of the black hole is going to infinity. So that's the setting in which we are doing this calculation. Okay, and how to interpret this at finite G Newton is sometimes a tricky question. So, but that's where the calculation. So in that sense, this is just a pure quantum field theory in a fixed background calculation. So we don't have to really worry about energies, divergences, and things like that. At least at the level of approximation that I'm talking about. Okay, so yeah.
If you assume the vacuum time energy, like will it dominate all of these terms, like from the contribution of all of the higher terms?
So that's always the question that we could always ask in any this thing, right? So if you have why are we not forming black holes when we scatter particles? So there is some UV regulation that is happening, right? So yeah, I mean there are many things to say here. So let me not say anything. Any other questions? So I mean, I'm actually specifically talking about the details of the calculation. In any place, is the chain of logic clear? That is what So the more conceptual, issues like what he's asking, they're valid questions, but let me not address them right now. The thing that I'm more concerned about is in the logic involved in the calculation. Is there any place where it was not clear? So as I said, there are two places. First ingredient is how we are fixing the initial state for the scattering in the sort of the potential, the Schrodinger potential problem, and that's where really the real assumptions are going in. And after that, you can think of it as just essentially a quantum mechanical scattering problem. So the stuff that looks kind of messy on the board is not that complicated. You can look at this. I'm essentially completely following Harlow, this part. So it's like, you can just go look at it. Okay, so, all right, so yeah, so I think we have to kind of wrap up this class because I think Apurva has a class here. So let me just say a few words about okay, so what we have really found is that the initial state that we put in here, as I said, is a vacuum state coming from, so there is the ingoing modes are in the vacuum state and outgoing modes are in a thermal state. Okay, so that's the initial conditions. And once you make that assumption, so whatever rationalizations we had for making that assumption, forget about them. But ultimately what it really is saying is that as far as the black hole is considered, there is a thermal atmosphere behind this angular momentum barrier. Okay, there's an angular momentum barrier sitting there, and there's a thermal atmosphere, and things are slowly leaking from behind the barrier outward. Okay, so that's the picture. So the standard assumption for why this thermal state is put in is the fact that you have a smooth horizon and you have some entanglement structure. Okay, the entanglement structure at this point is identical to that of flat space. So that's why we are doing this. Okay, if the entanglement structure here is the same as flat space, if you look at just this part, it should be a density matrix, thermal density matrix. So that's what we are doing. But so it's a question that people have wondered whether it is really that is the real answer. So there is an interesting suggestion by Toft, which I think is worth talking about, that if you put a cutoff right before the horizon, so that your potential basically looks like, there is a potential wall here and then you have stuff here. So then you can think about the modes that live in this barrier here, right? In this well. So this well, so now this is the analog of let's say Planck's calculation of black body, which is that you count the number of modes that live here and then you see whether they are actually giving rise to thermal spectrum or not. So this calculation surprisingly can actually reproduce some of these features, including entropy and area and all that, up to order 1 coefficients. Okay, so this idea, I'm not going to go into it in great detail. Stretched horizon is the name for this idea, and in various incarnations it has played a role in many contexts in our discussion in the last 30-40 years. So, but yeah, so this is also something. So it's somehow an interesting fact that even if you have a smooth horizon or if you have a brick wall, you sort of get the same answer. Okay, so that's something that I think is worth noting. So, but anyway, so that's one observation. And yeah, so another thing is that as you notice, the height of this barrier is proportional to L square, as I wrote down last time. Okay, which means that the particles that leak off to infinity, you know, those that are tunneling through this barrier, if you like, those are the ones which are generally of low L. Okay, so yeah, so this is a picture where I think it is really legitimate to kind of think of it as tunneling. So people sometimes also talk about Hawking radiation itself as sort of a tunneling, where you have a particle that is entangled and one falls into the horizon, etc. Those pictures are, you know, there are some calculations which people do which are somehow legitimizing it, especially from Parikh and Wilczek, but I still think that they are a little weird, because you note that the wavelength of these particles is large. They are of the black hole size. So which means that falling into one of them, so people usually use this phrase that, oh, there is a pair production of two particles at the horizon, one is positive energy, one is negative energy, the negative energy guy falls into the black hole, so this state you can think of as having got its energy from the black hole and then it radiates off as a positive energy particle to infinity. So this picture is not that easy to make sense of, even though if you are interested you can take a look at these calculations or, you know, there are some papers by Parikh and Wilczek which try to legitimize it, but I'm not convinced. So, but on the other hand, the distinction I wanted to make was that this is a second tunneling that I'm talking about. This tunneling is a real tunneling in some sense. It's genuine quantum mechanical tunneling between, you know, across this potential barrier. Okay, so there is nothing particularly strange going on. It's just quantum mechanical tunneling in this barrier. But if you want to kind of pictorially view the black hole as, you know, this pair production and so on, it's a little bit harder to make it really tight. Yeah. Yeah, I think that's a good place to stop, I think, because I think today's class is, again, you know, I also want to stop a little bit so that Apurva has some time. So, any questions?
So,
Yeah.
if an infinity observer and Minkowski has to observe the Hawking radiation,
Right.
I have to show this in the Penrose diagram. I have to attach a Minkowski patch at the edge.
So you mean like, let me draw that picture here again, because this is kind of a very important picture. So this is our shell, and the guy, you know, so the Minkowski guy, very roughly speaking, is, you know, R equal to constant lines in this Penrose diagram will basically be curves like this. Okay, so he is somewhere far away, and we are assuming that it is sufficiently far. That's all. We are not being too precise about it. So we are standing, some guy standing somewhere here.
No, but I'm just saying that if I have to depict the Hawking radiation coming out of this diagram.
Yeah, so that will be here. The Hawking radiation will be coming out like this. So this is where the observer is standing and he is detecting them, in principle.
So the observer is standing in the Minkowski space, right?
Asymptotically, you know, this is, note that this is asymptotically Minkowski space. So far away it looks like Minkowski space. So here we are essentially Minkowski space. So, and the guy is standing there and he's collecting Hawking radiation if he wants to. So yeah, so we don't have to attach anything else. Here the time taken to reach infinity in Minkowski space is infinite. Okay, especially if you are talking about Hawking radiation in the context of black holes and ADS, that's not the case. So black holes, you know, like you can, you know, there is an infinite amount of volume at the asymptotic region of ADS space, but there is not an infinite amount of time. You know what I'm saying? So if you send radiation out, it will come back in finite time. Okay, so that's an important distinction between flat space and this thing. In some sense, flat space carries its own, you know, heat bath to which you can send the radiation off. Okay, so there is enough phase space in the infinity of flat space to contain any amount of Hawking radiation that you send in. So that's not the case in ADS. ADS is more like a box. Okay, yeah. So any other question?
Sir,
Yeah.
what is the high energy modes escape, right?
Sorry?
What is the high energy modes escape?
Why?
Like it's in the black holes.
Okay, so there are multiple. So the modes that you're seeing as a result of Hawking radiation are generally speaking highly redshifted. But because of the fact that they have this Planckian distribution, it means that there is some low probability for you to detect even high energy modes. That is there. But that's not what this is. This is, generally speaking, you would always see low energy modes.
Like at the Minkowski, you see the low energy modes. But they initially started as high energy.
Yeah, you initially start at high energy modes, but at future infinity you won't see them, right? Those are modes which are coming in from here, if you like. If you really want to phrase it as a high energy mode, it will start from here, and you have to kind of start a little bit like here, and it will go like this.
But for a black hole to completely evaporate, you have to see all the modes. Like all the energy should evaporate in infinity.
Yeah, but it can all evaporate at low energy modes, right? Why should it evaporate as high energy modes of this kind? These are incoming modes. These are incoming modes, and the point is these incoming modes can be used to justify or rationalize the assumption that I made about the nature of the state here. That's what I was saying. So these are incoming modes. So note that this is a space-time or a universe in which there is only one collapsing system and it forms a black hole. So which means that at late times there is nothing else. The only thing that can come from this system are basically the things that can come from this radiation. That's it. So even if you had, let's say, some, you started off with some radiation which was going in some arbitrary direction, whatever part of the collapsing system, it would all be collected somewhere here, right? But if you are at late times here, there is nothing else. It's only the black hole's eventual radiation is the only thing that is there. All the quasi-static phenomena have settled down. There's nothing else. So the black hole is formed, and then if you detect something, it's produced by the black hole due to Hawking radiation.
What happened to the initial low energy modes which also fell into the black hole? How will they come out?
Whatever fell into the black hole, etc., we don't know, because that's why there is an information paradox or something like that, right? So whatever was the structure of the things that went into the black hole is not visible here, because all that is really happening is that there is a thermal spectrum which is slightly modified by this angular momentum barrier. So that's part of the information paradox if you're worried about that, because what you're really seeing is really a property of the black hole. That's what you're seeing.
We are not claiming the black hole will fully evaporate.
So the question of what happens to the real final state is something you can worry about. But note that this is actually happening at for most of the times, the history of a black hole, you're actually in fairly low curvature regimes. So this calculation, at least if it stands as it stands, it is perfectly valid throughout the history of the black hole, essentially. So let's say that it's only at the very beginning when there is some quasi-static phenomena, at the very end maybe when Planckian physics kicks in. Those are the only places where there is any real challenge to bulk effective field theory or gravity, etc., standard things. So, but in between all of these things, this is all highly low curvature regimes. Okay, so these are all low curvature. So for instance, even astrophysical black holes are low curvature because we are talking about Planckian curvatures. So compared to Planckian curvatures, astrophysical black holes are perfectly, there's no reason. So you might get, spaghettified, and your lifetime inside the black hole is actually very small by human scales, but it's nothing compared to Planck scale. So they are fairly low curvature. So let's consider, the possibility where the black hole is even bigger. Most of its lifetime, you can make it precise. Its hierarchically a high amount of lifetime is spent when the black hole is at, big. The reason is that Hawking radiation basically becomes lower and lower temperature as the mass of the black hole becomes bigger and bigger. So it takes longer and longer for the higher mass black holes to evaporate. So most of the time black holes is in low energy regime. Okay, so the time scale that we're talking about are not even universe age. They are trillions of years, not even trillions. I think, huge amounts of time. I don't even know. So let's just say some Google amount of time, So, you can make it precise, but it's a humongous amount of time. Hawking radiation, so and at the final end result, we expect that it is thermal radiation. But it has to be mostly thermal radiation. You know what I'm saying? Because it has to be mostly thermal radiation. At the end, there is some drama, but that's not enough to get rid of the information paradox. So the question of what happens to the initial modes that went into the black hole is some other question. We don't have an answer to that at this stage. Yeah. Any other question? Okay, so if you have any question, just send me an email or something. I think you can stop.